Okay, we're going to look at log functions, and to introduce this, recall what the exponential function looks like, and we're using a generic case here of a to the x. So a could be any number, could be 2 to the x, could be 3 to the x, could be e to the x. Either way, we know it's going to pass through this point 0, 1, okay, right here. So if we were to reflect this over the line y equals x, then we would have what we call a log function, where we have log base a of x. Okay, this is the inverse. All right, again, it's a reflection over y equals x. If 0, 1 is on the exponential graph, we know that 1, 0 is going to be on the log graph. Okay, so recall that we said if you were to take the log of 1, doesn't matter what the base is, that is going to be 0. So that is why we know it's passing through the point 1, 0. So some facts about our general log graph here with the base of a. We know the domain is going to be all positive numbers. Okay, we said we can't take the log of a negative number or 0. The range would be all reals. Notice on the graph here that it is not going to hit the y-axis. That means we really have a vertical asymptote at x equals 0. And we talked about how the x-intercept is 1. Okay, so all of the transformations we talked about before, where we can shift things up or down, left or right, we can stretch or shrink both vertically, horizontally, all that stuff applies to this type of function as well. Okay. Alright, so let's look at the special case of e to the x, okay, an exponential function here that is graphed for us. And if we were to reflect that over the line y equals x, then the inverse graph is what we call the natural log of x, which is abbreviated ln of x. Now this is really log base e of x. On the previous slide we talked about log base a of x if we have the exponential function of a to the x. Since this is e, remember e is our irrational number, it's about 2.7. So we really are dealing with log base e. But we never write log base e. We always write it as ln of x. Okay, so IB is really big on e to the x and ln of x. It's absolutely critical that you know that they are inverses of one another. Okay? So since they're inverses, if we were to look at something such as the natural log of e to the x, well, this is the same as writing this as log base e of e to the x. And recall we said earlier that if these bases are the same, you're just going to have whatever the power is. Okay? So think of it as they're going to cancel each other out, and then x just falls down. Okay? Likewise, if we have e raised to the natural log of x, this is the same as e raised to the log base e of x. And this is a very similar situation as what we saw up above, in that we have the same base here, and so if that's the case, everything is going to simplify down to just x. Okay, so again, think of it as the e and the ln, they wipe each other out, the x just falls down. With this last one here, we could actually generalize and say a raised to the log base a of x is just going to be x. So again, it's the idea of these bases being the same. Okay, we are looking to evaluate the following. Not allowed to use a calculator. So these are really quick. There's virtually no work to show. So we're just using some of the properties of logs that we've been talking about. So the first one, we have 8 raised to the log base 8 of 2. Well, notice how these bases are the same. When that's the case, you're just going to have whatever you're taking the log of, so that would be 2. Okay. Number 2, the natural log of e raised to the 6th. Well, because ln is a log, this 6 you can put in front and multiply by the natural log of e. And we're going to review our log properties in the next video. But the natural log of e, since those two are inverses of one another, that's just 1. So you have 6 times 1, so your final answer is just going to be 6. You could also think of it as the natural log of e, they cancel each other out, and then the 6 just falls down. Next we have e raised to the ln of 7. Well, e and ln, we said are inverses. All right, they wipe each other out, so that 7 would then fall down and become your simplified answer. The last one here, we can use our exponent rules and rewrite this as the natural log of e raised to the negative 2. And then just like example number 2, those wipe each other out, and you're left with negative 2 for your answer. Okay, what we're looking to do here is solve an equation. Okay, so we're looking to solve for x, and we notice there's an e in this equation. Well, remember that e's inverse is the natural log. So to wipe out this e, we can take the natural log of each side. Okay, of course, what we do to one side, we must do to the other side. So we're going to take the natural log. We don't want to use the common log. We want to use the natural log since e and ln are inverses. Well, those are going to wipe each other out, and you're going to be left with x equals the natural log of 5. Now this is a nice exact answer. Alright, you could also throw it into the calculator if you were allowed to use a calculator and get an approximate answer of 1.61 if we were to round to 3 sig figs. Okay, so 3 total digits is usually what we mean by 3 sig figs. Okay, that's how IB wants you to round in any problem where you don't have an exact answer. Okay, here's one more equation to solve, but this time it has a natural log in it. So what we're going to do here to solve this equation is we're going to recognize that we have a natural log in the problem, and we have to recall that e as a base will wipe out that natural log. So I can drop an e underneath each side here as a base, and that leaves me with x equals e cubed. That's a nice, clean, exact answer. Or, if we were interested in rounding our answer to 3 sig figs, x is approximately 20.1 if you used your calculator. Okay, so let's practice finding the inverse equation. So we're given f of x equals e raised to 3x. We're looking to find the inverse equation. So remember, f of x is really the same as y. So when we switch x with y, we're left with x equals e raised to the 3 times y. So we see an e inside here. So recall that we are trying to isolate y. So we need to get rid of the stuff around it. So because we have an e, we're going to take the natural log of each side. Okay. We said how the reason we're doing this is because we know ln and e are inverses. They're going to wipe each other out. So we have the natural log of x equals, now this 3y will fall down. So we would then just divide over our 3 and we're done. So our inverse equation here, we can write this as 1/3 ln of x, or just ln of x all over 3. Okay? Okay, one more here. Now we have our f of x equal to the natural log of 2x plus 1. That whole quantity is what we're taking the log of. So again, we're going to switch x with y, and we are looking to solve for y. So we see that there is a natural log in the problem here. We have the natural log of the entire right-hand side. So we're going to drop an e underneath of that entire right-hand side, and then if I do it to one side, I must do it to the other. And again, we're going to do that because we know e raised to the ln. They are inverses, so they will wipe each other out. So I'm left with e to the x equals 2y plus 1. So then I would have e to the x. I can subtract over my 1, and then I could finally divide by 2. Alright, and that'll allow me to get y alone, which is my inverse equation.